My name's Richard Luca. I'm employed with NHP, and I've had a few different roles over the years, over the last 21 odd years. My current role, I'm working with consulting engineers, engineering firms on projects and solutions according to specifications. So today we'll be looking at a hidden but critical vulnerability in modern healthcare facilities, and it's the electrical infrastructure. I'll discuss why we should move beyond a simple main switchboard model and transition to a site-wide energy monitoring system. So the agenda is split up into three sections. We've got first section, which is understanding power quality. So that's looking at harmonic behaviour pretty closely. Then the impact of electrical systems, compliance monitoring. So looking at some loads, affected loads and issues caused, and some compliance requirements there according to standards. And then the analysis, mitigation and continuous improvement. So utilising a site-wide monitoring system. So this image here represents the journey that most hospitals are on today. You've got a facility manager looking at an aged switchboard. You've got a lot of old, obsolete systems, switchgear protection devices, and no visibility into what's going on in the network. When a problem happens, you're sort of chasing your tail, and you're often just reacting to a lot of issues. So the question is, how do we go from this to something like this? It's not going to see your travel agent. It's utilising a site-wide power monitoring solution, a smart system. So now the facilities team can look at it. They can look at real-time information, trends, harmonic information, compliance requirements, energy reporting, historical alarms. So everything has become visible now. And with that data-driven platform, we can achieve compliance. A resilient network drives efficiency, safety, and all that ties into trust and confidence. The first section, understanding power quality and harmonics. Now, the energy transition, it's transforming hospitals into a complex system now. We generally think of supplies as, you've got a mains utility supply and a backup diesel generator supply. Now it's much more complex. We've got microgrids. We've got EV charging, rooftop solar. We've got large-scale battery energy storage systems. So all this, the electrical baseline has flipped from having linear loads. So now we're flooded with non-linear loads, which are polluting the network. So this is a risk for a hospital. So you can't afford any downtime. When we talk about linear devices, we're saying that the loads that we're connecting to the network, they're drawing a current sinusoidal waveform, which is similar to the utility waveform at 50 Hertz. So there's limited distortion there. We may have a phase shift, which is going to create inefficiencies, and that can be corrected with power factor correction capacitors. But all the load current is drawn at the fundamental frequency, 50 Hertz. And examples there, induction motors, incandescent lights, resistance heaters. And if you want to think about it another way, you've got your garden tap at home, right? If you connect a hose to it, I can control the amount of water coming out of that tap. And the water is essentially the current. And I'm controlling through the valve the amount of pressure through the hose. So the pressure is the voltage. So there's an almost linear relationship there. But most of the loads these days, they're all non-linear, right? They're all driving efficiency, switch mode power supplies, a few examples there. Sensitive medical devices, UPSs, LEDs. So what happens when we connect these devices on the network? They introduce in harmonic distortion, and they're odd multiples of the 50 hertz waveform. So when we superimpose that on the 50 hertz wave, we get a really distorted wave propagating throughout the network. And the common example there, bottom middle, is a drive schematic where you've got an input rectifier stage. So the diodes are switching, rectifying the voltage, and the current is being reproduced to control the motor. So in that rectification process, you're getting all these anomalies or harmonic distortion occurring. And you can see that in the far right there. So really distorted wave, and the harmonic spectrum, you can see the fundamental frequency, it's quite high. And then you've got these other odd orders introduced in the network. The bottom left shows a waveform of an MRI machine. So there's big power amplifiers in an MRI machine, and there's a lot of energy that goes behind that process, and there's a lot of noise produced in the process too. So in our quest to save energy, we install VSD chillers, LED lighting. Hopefully they're not the cheap and nasty ones that blow every 6 months, but we install all these products to achieve the benefits of reduced energy, but at the cost of harmonic distortion. There's 30–40% in the system. And they're the originators, but the prosumers producing harmonics and also consuming harmonics. We've got MRI machines, digital X-rays. These are very sensitive devices that require almost perfect sinusoidal waveforms to operate. If not, then you could risk glitching, artifacting, losing synchronization on those units. So it could mean a wrong diagnosis on a patient. So the clash is when you've got HVAC plant producing a large sum of harmonics, that's flowing through the network and causing issues down to a cardiology wing. System impacts and compliance requirements. So we're going to look at some impacts now with harmonic distortion, and it falls under broad category of increased operating costs for the facility. We've got an increased RMS current draw. So there's a factor applied, increase in THD. We apply a factor on the THD for the facility. Overheating of the standard transformer supply. So with transformers in their makeup, the metal construction, the iron, copper losses, with increasing THD, these things need to be derated. So 1000 kVA transformer may be only acting like a 700 kVA system. Conductor losses. So we've got, everyone knows the I²R losses in a conductor. The square of the current times the resistance will give you the power loss. But there's also skin effect. Introduce these harmonic distortion in the system, additional frequencies, has an effect. So we've got a cable here, the current that's flowing through the cable in red. In blue, we've got a magnetic field around that cable that's pulsing, and then we're introducing eddy currents around those magnetic fields. So what happens is the current through that conductor, the eddy currents push the current away from the center of the conductor to the outer edge. So this is called the skin effect. It's quite well known, bus bars, cabling, and that cross section in red, it shows you, it's abbreviated by delta, it shows you the skin depth of a conductor. So with increasing harmonic distortion, that skin depth reduces. So a lot of the current is forced to the outer edge of that conductor. So again, there's increased operating costs in the form of losses. Poor power factor, you can see straight away, true power factor and displacement power factor of 50 hertz, they can be equal if there's zero harmonics in the system. But the blue waveform down the bottom, we see a displacement power factor, roughly 0.96. And the purple waveform, that's our true power factor with harmonics in the system. So there's a differentiation there. With harmonics, you get a considerably less power factor in the system. And that's creating a lot of inefficiencies. With all that, points 1 to 4, we need to upsize now, oversizing cables, transformers, protection devices to handle this increased wasted energy. And you can see down the bottom formula, with a 40% THD in your plan, there's an 8% increase on RMS current. With 100% THD, there's a 41% increase on the RMS current. Another aspect is the positive, negative, and zero sequence effects. So each order harmonic is given a sequence. Now, without going too detailed into it, 50 hertz is a positive sequence. It's rotating in a forward direction. Second harmonic, that's rotating in the opposite direction, whereas a third harmonic has a zero effect. So what that means for your system or your plant is you've got excess energy in the system, rotational forward. Reverse effect, you can see in that load torque of the motor. If we're introducing harmonics in the system, it's affecting the load torque of your motor. So the resultant load torque, you can see the dips and the peaks there. So that's actually changing the magnetic fields in the motor. The zero sequence, those currents in 3 phases, they all add up into the neutral. So that's not ideal. So overall for the facility, we're looking at higher electricity costs, lower system efficiency, and increased capital expenditure. The next set of impacts fall under reduced asset life and maintenance. So it's where the equipment ages faster than expected. And we've already spoken about overheating the transformer and supply equipment. But harmonic resonance, it's a real thing. If you've read any books about it, or the physics book talks about the wine glass experiment with the opera singer. You heard about that one? But everything in life resonates, so it's got a resonant frequency. So if we look at a wine glass, its resonant frequency is just over 500 hertz, which means at that frequency, if someone can raise their voice that high, they'll end up shattering the glass. That glass will absorb all the energy at that particular frequency. Its atoms start to vibrate and it will shatter. Back in the electrical world, the same thing happens. When the source impedance and the load impedance are matched, and there is a particular harmonic frequency, at that resonant frequency of the system, we'll get a really large spike in current voltage. And what you see here was a case study where a site had 2 500 kilowatt drives, power factor correction system close by. There was always in alarm mode, wasn't even operating. And PLC system rebooting, network comms issues. So logging this revealed that, there is a resonant condition here. We've got just over 800 volt spikes on a 415 volt system, and current just over 1500 amps spikes. So this was happening randomly, 2 a.m., 3 a.m. in the morning. So without logging, you won't be able to detect this without just going to replace your failed components. So speaking about that, telco, timing systems, malfunction of equipment, computers, UPS, sensitive electronics, all these components, they need a precise waveform, a clock frequency. If that's disrupted, you get a lot of issues with sensitive electronics. I mean, 1.5 kV is generally the limit for these sensitive electronics. A recent site inspection I had in an airport with the baggage handling system that was failing intermittently. Did some initial inspections and couldn't really find anything. And the facilities manager said, "Oh, don't worry about it," because the problem just went away by itself. And that's the issue with harmonics. Sometimes it's there, like a ghost, and sometimes it's not. So without monitoring these things, you won't know how to go about fixing them. So for the facility, there's more frequent maintenance that we put down as scheduled maintenance, increased replacement costs, and unplanned asset failures. We can't have that. And the last set of impacts fall under the operational disruption and downtime, where the equipment doesn't operate as expected. And I've gone through points 1 to 3 already. A lot of these issues have dual consequences for the facility. But point number 4, another site I attended, a commercial property, the client was experiencing a lot of appliances blowing. We couldn't exactly figure out what was going on, but we knew that it was being fed by a few hundred meters down to a shared transformer. It was being shared by a few different businesses, and one of those businesses was a large sawmill. And in the afternoons, they'd start up a big bandsaw. And we found that, okay, there's a lot of transients flowing through the network, distortion coming and affecting this business. So he went back to the utility and requesting some more investigations. We've got generating stability and frequent starting. The recent one, a phase failure relay, constantly calling the generator due to a phase imbalance. Protection devices nuisance tripping. Now I'll put these two waveforms in here. So the green one, green is good usually. So if anyone knows the crest factor, it's the peak to the RMS figure. And in a pure 50 hertz wave, the crest factor equals 1.4, thereabouts. In the red, if we've got a highly polluted waveform propagating throughout your network, you could have a crest factor of 3 or greater, which means you're going to have a really peaky waveform. So coming back to the real world, for your installation, if you have a thermal magnetic breaker, and everyone knows it's a bimetallic strip that's operating and bending according to the amount of current passed through it, and it's just responding to the heat. So we're just looking at the total current coming through, including the harmonic distortion, increased RMS. So we're going to get nuisance tripping if it is a thermal magnetic device. Whereas electronic breaker, it's using internal CTs. So we're sampling at a particular frequency, getting the true RMS waveform, and then detecting on that waveform. But under the standards, there's a standard 60947 part 2, which is the multi-case circuit breaker standard. And there's a section there where the circuit breakers are tested to a particular harmonic waveform. And it's roughly about crest factor, roughly about 2.2, with overall THD roughly 50%, 50 to 60%. But if you get a really high crest factor, then that electronic circuit breaker is just seeing a reduced waveform, not the actual true peak, because of the clipping of the internal CTs. We get saturation. And that's no good because it could lead to more catastrophic events. Increased neutral currents. So there's extended downtime here, cancelled procedures, and overall reduced system reliability. There's one more important aspect I want to talk about, and everyone knows about EV. Who drives an EV here? Right. Tesla? All right. So NHP's invested a bit of time in this area with electric vehicles and seeing the harmonic performance come out of the vehicle. So we know you get the charger, the cable, plug it in the car, AC rectifying in the car to charge the batteries. So the onboard charger in the car, every make and model is different in its makeup. It's got different components. So which means the harmonic spectrum is different for every model and the phase angles are different. So for your facility, if you're looking at some sort of fleet, having diversity is good, where you've got a lot of different performance coming from the OBC. The phase angles are cancelling out to neutralize the harmonics. But where it's not so good, if you're driving a Tesla and you're all plugging in your Teslas at the same time, the vectors are quite similar, which means they add to the network. And that's a problem for critical infrastructure because it's adding something that we haven't accounted for. If you do need more information on this subject, like I said, NHP's got some information, so we can discuss that. I'll have a QR code at the end as well. But just looking at some compliance requirements, every state's going to be slightly different in how they operate. Victoria, in terms of power factor limits, they want you at about 0.8. I think Queensland is at about 0.8, the same. That blue table, it shows you the reasons why. At a power factor of 1, the installation is drawing 100 amps. But if we're reducing our efficiency to 80%, 0.8 power factor, we now need 125 amps of current to service the same load because of the wasted energy in the system. So increase of 25%, I squared R losses over 50%. So the utilities don't want you, or don't want all businesses running at a very low power factor, because they'll have to beef up the infrastructure and costs go up for them too. With the IEC 61000 standard, under voltage harmonics, the limits are 8% for the facility. That's in IEEE 519. But that's at the PCC, the point of common coupling, where the low voltage side of the transformer utility connects to the consumer's load, generally the main switchboard. With the current harmonics, the IEEE 519 standard, we're looking at this, this table here, which gives us the short circuit ratio and the load current. So for the facility, we'll work that out, move it across, and we're given a total demand distortion limit for the facility at the PCC. And for any power generation facilities where you've got renewables that are generally over about 10% of the load demand, you'd need to comply to the lower limit. So the traditional approach, we put an energy meter at the main switchboard and we see, okay, 4.2%, it's healthy, it's all good. And we see clean energy. But there's a lot of blind spots in that approach. Without monitoring individual loads, we don't know if there's harmonics that are infiltrating, propagating throughout the network and affecting other loads. So this can be causing a lot of issues deep within the network. And by the time it cancels out at the PCC, everyone thinks it's okay. So analysis and continuous improvement. So this topology here shows a site-wide power distributed approach where we're monitoring, and seeing as though we're talking about hospitals, I've stuck with the same theme here. So we're calling the level 1 incoming power the heart, right? So using, say, a Q800, it's monitoring for sags, swells, interruptions, events, class A meter, tested to the standards. It'll give you, and you'll be able to see from a site-wide perspective, everything that's happening on the network. If there's any anomalies, you can drill down further. So from there, we look at the arteries, so the outgoing feeders. So we're putting modules beside the circuit breakers. So now we can have virtual monitoring. So this system can actually pick up the circuit breaker status without tying into the auxiliaries. Then the distribution panels, which are the capillaries. So this is a branch circuit monitoring system. We're tracking specific loads here, HVAC, lighting, diagnostics, IT, and we're seeing everything from a fine load perspective. We can also get usual water, gas, temperature, any of the field devices we can put on the network too. So all this is RJ45, plug and play. Back to a web server, we can view it on the web server, or back to your central head-end system. And that's what it looks like from a component level. So inside a DB on the right, you can see the modules, and we can have various CT connections on the individual loads. And the beauty about this system is the accuracy class is maintained at class 0.5 throughout the entire network. So traditional wiring, when a contractor goes to wire your system, the spec may call for a class 0.2 meter. By the time the contractor wires it, the whole system's probably a class 1. So you've got to be careful in how you install this system. But this system here, it's maintained at 0.5 accuracy. And using special CT. So conventional CTs are accurate down to 10%. If they go down below 10%, there's a lot of inaccuracies. Whereas these CTs here, the accuracy is maintained all the way down to 2%. So this system daisy chain back to a display or a gateway. that gets fed back to the head-end system. And that's what it looks like when we interrogate the system. We see a snapshot. Okay, we can look at the currents on the individual phases, what the neutral's doing. So from a site-wide perspective, we've got visualization from the whole plant. We can drill into individual monthly energy consumption. Are we going over a particular threshold? Do we need to plan some sort of maintenance plan the next month when we've got a reduced consumption? Drilling down even further, so we can see individual boards themselves. So someone might say, okay, are these boards in green? You know, they're a lot less energy. They're the same boards, same loads. Why is it less energy than the blue? You know, is there blocked filters, you know, broken coils, or is there something wrong with the HVAC compressor? We can put floor pans here. Okay, click on each individual section and drill down even further to the specific loads. So back in the head office in Melbourne, we've deployed this system so we can see exactly where all the power is going. And one observation was that no one likes the standing desks in the office. So everyone prefers to sit, and we can see that by the consumption at those desks. So for the facility manager, he's probably thinking, I can take those desks down and put some pot plants there. So looking at the THD now, so straight away down the bottom, I can see the blue chart, the 3rd, the 9th, the 15th, the triplet harmonics are quite high on this load. And the chart on the right, that's the power factor. On the 3 phases, look at the 3rd phase, something's happening there on the 3rd phase. That warrants me to investigate what's happening on that phase. From a site-wide perspective, now I can look at these trends over the day, the week, the month, and say, okay, why did we spike at this time? Or if you want to put that into AI, ask AI to, you know, quiz it for you. But yeah, for a facilities team, they can start to decide what to do and act before something happens. There's a trend here. We need to know what's going on. I'll relate this back to a recent blood test that I had. And the last blood test was about 3 years ago. And comparing the results now, some indicators were slightly less. And my GP said, all right, maybe you need to, you know, increase your red meat intake. So straight away, I went to the butchers, said, yeah, I want one of those. I want 10 of those, 20 of those because they're on special. So I started to, you know, invest in that for myself. And that's the same too in the electrical world. You need to monitor these things and track it. In another 3 months, I'll have another blood test and see, you know, am I going to get back to where I was? I need to invest out of my own pocket, my time, and it's all about the health of the infrastructure. So once all the hardware's there and we've assessed it, now what do we determine with the traditional approach? We've got this big bulky APF system that's connected to the facility, but its main purpose is to limit the harmonics at the PCC. We know what a PCC is now. So compliance check, okay, walk away. But what happens is deep within the network, on the right-hand side, you've got your HVAC plant. We've got harmonic distortion, which is propagating throughout the network. And you may have a large run of cable, 270 meters, to this HVAC plant. So local compensation makes sense for that because it will save all that distorted energy from flowing in that particular site. The same thing with all your sensitive medical equipment. Local compensation, we're effectively trapping the harmonics locally from propagating throughout the entire network. And also PCC changes as our source changes. So again, it goes back to the standards there. So we need to make sure that we're compliant at the PCC. So a quick 3-step action plan is assess, segment the loads into groups, critical, to perform your gap analysis, and then distribute the sensors in those locations and put it all back to the gateways and back to the network. But that's not enough. We need to look at the data, optimize, and then mitigate. So if there's a hotspot in the system, we need to be trending that, set alarms, notifications, because that could mean later down the track that there's some unplanned outage. So just to wrap things up, so we've spoken about compliance. It's not just about ticking a box, it's upholding the reputation of the facility. Resilience. You want to prevent cancelled procedures, right? Reduce downtime and data loss, and then driving efficiency too. But it's all about safety. So there's the uninterrupted operation of critical medical equipment. And that all ties back to the trust and confidence in the facility. So we want a reliable, resilient, and future-ready environment. So thank you for your attention. If you needed more information, please scan the QR code, and we're happy to discuss more. We'll send some further details to you.